So let's wait the people to connect. Audio should be fine, and I am still sick. I have one concurrent viewer. Let's wait for someone more to connect. We have two. We will start now with a cycle of 3 lessons on microcontrollers. And in particular, we will see this board, the Arduino microcontroller, the Arduino Mega actually, or a clone, which is perfectly fine given that the only thing that this board contains is basically a microcontroller and some passive component. This cycle of lectures basically follows what I have taught already in the course of Sistemi Operativi at the bachelor level. So like I perfectly understand the students that had already taken that course, that if they don't want to skip the lessons. But anyway, the exercises, in case they didn't do them back then, well, I invite them to do them this time. Good, Marco, good. Marco says that he wrote that I started. Yeah. Now I'm still babbling, let's wait in a while. There will be people appearing. All right. So said. Now we start our story with the Arduino microcontroller, or the AVR microcontroller, because this is the chip that you find on the Arduino Mega. As always, we go a little bit to inspect the systems that we are utilizing. Now, of course, the concentration of messages reaches the peak when I'm giving less. I don't know if you ever had experience with electronic devices, but in case you didn't, well, this is the first time that someone is talking to you about this thing. Now, in general, the chips, in particular the CPU on the computer, is a digital device that communicates with the other peripherals, with the memory or with other devices, for instance the USB controller, through a set of digital pins. Digital pins is a connector, or is a pad, is a piece of metal on the chip that can either produce a voltage between a logical 0 to, which is either a logical 0 or a logical 1, or it can read a voltage that it's either a logical 0 or a logical 1. In particular, an old style CPU, but also the modern ones internally, communicates with the rest of the system through a pair of buses. What is a bus? Or to a bunch of buses. A bus is nothing else than a collection of these digital pins that have a very specified task. In particular, we're going to detect a unidirectional bus, which is the so-called address bus, whose task is to put in output the current address of memory from where the CPU wants to read or to write. In some architectures, this bus, these pins, can be put also in high impedance mode, which means they can be isolated from, can be just kind of disconnected in case some other device wants to use the set of wires, for instance, the video card that wants to read from the RAM of the PC. So in this case, the address bus can be isolated. But in general, you can think of it as a bunch of wires that output a number, a digital number. We have another bus, which is the data bus, which you see here, which is the bidirectional, and it's a bus, so it's a set of pins where the CPU writes the value it wants to read, or it wants to write in memory, or from where it reads the value that it wants to get from memory. So therefore it's bidirectional. Clearly this bunch of pins, of course, the modern CPUs, they have much wider buses, which means with many more wires, are not sufficient to determine what the CPU wants to do, because how do you know with only these connectors whether you want to read or write from memory? You need typically another variable, because every of these pins, you can think about it as if it was a 1-bit variable. You need another variable that tells you whether you want to read or to write. And in addition, you might need additional control pins, additional control flags that can be either input or output, that are used to orchestrate the behavior of the address bus or of the data bus in the rest. As an example, if the CPU wants to read, well, we will need a Boolean variable, which we will find here in this pin as the, so I said read. Read with the bar on top means that it's active low, but in case the CPU wants to read, well, what we expect to do is to put on the address bus the number of memory, the address of memory from where it wants to read. Then it asserts this read pin, so it says I want to read now, and then it waits a bunch of cycles until the memory responds by putting on the data bus the value of memory, that the value that is stored in the memory location, which is asserted on the address bus, right? So this is in general, we have a bunch of pins for dealing with additional tasks, and that can be used, as I said, to orchestrate the behavior of the other two buses of the CPU. Of course, we have additional signals, like the clock signals, that should be provided from the outside, typically, but some microcontrollers have an internal oscillator. We have additional pins that control the interrupts. Interrupts are asynchronous events, and so on, that can alter the behavior of the CPU while executing its standard program. Classical example is you pressing key. Normally, this was the CPU. We focused in this slide only on the CPU itself, right? Only on this chip or this bunch of chips in the past that constitute, let's say this way, the execution unit of our machine. But in general, the CPU alone is useless. You need always to couple it with a bunch of other logic pins. And this slide, you see a simplistic 8-bit microcomputer with a bunch of chips constructed around the Z80 CPU, where we can see that there is a memory chip. We can see that there is an EEPROM, which stores the non-volatile program. Basically, can it be the operating system in the old times of the CPU, so it's the program that the CPU reads when it's just started. We observe that the address bus over here is typical. Well, it's not mentioned, but it's typically shared between all the pins, all the same peripherals, which means that the line the bus line A0 goes to the bus line A0, both of the RAM and both of the EPROM. While the higher order of addresses, they are typically demangled by a certain logic that decides which of the two chips to enable based on how the memory is mapped. On top of it, we have, well, beside the CPU, well, this is the bare minimum, but this, our architecture wouldn't be able to communicate with the outside world, so it will be basically a closed box computer. In order to interact with it, we need to couple it with a parallel input-output, which is basically a digital port, which you see here, and the UART, which is a serial port, which is here, that they once again communicate. They are typically either memory mapped or they appear as memory locations to the CPU, still by playing with the decoding of the address bus. So like basically by having some logic that treats the highest pins of the address bus and decides which pin to enable, while the low pins of the address bus are devoted to assigning the address within the chip. Now this is an ancient architecture. A more modern architecture is the one that you see here. Well, where basically modern architectures we have that the CPU doesn't talk directly to the memory, but the CPU talks with an internal cache, with an internal memory controller, with an MMU, that in turn outputs commands for the RAM, which is still an address bus, but this address bus doesn't go directly to the memory, but gets let's say orchestrated by another chip in between, which is called typically the North Bridge, that manages the memory. So it's like we have an additional, let's say, intelligence between the CPU and the memory that orchestrates this precious shared resource, which is the RAM, that can be also used autonomously by other smart cards that we might have. Nowadays, the North Bridge is typically, or was typically, responsible of the high-speed operations, while we have a South Bridge, which is a slower chip, which is in charge to deal with the kind of less fast peripherals. But if we focus on microcontrollers, we have to consider that they pretty much reflect the behavior of old CPUs, which in the end is the behavior that you find also inside modern CPUs, only that in order to design hardware which is not going to frequencies that are skyrocketing, like in the order of gigahertz, it's much better to work with old style logic and with old style systems, and the principles stay and they work and they are just implemented inside the chip. Like as I mentioned before, it's interesting to see what happens at signal level when the CPU wants to read from memory. Remember that inside the CPU everything is orchestrated by a clock, which is basically a square wave where each transition determines one epoch in the CPU time. When a CPU wants to read from memory, well, what do you expect it to be? Well, we expect that the CPU first writes on the memory bus, which means assert a memory address on the memory bus. Then probably it will have to pull down a bunch of pins to say that what actions it wants to do with the address that it has just set. In particular, in case of the Z80, it will put down the pin memory request, which means I want to access the memory, and it will put down the pin read. And then after you have done that, you typically have to wait a couple of some little time for the RAM to respond and to put as output, so this is the timeline, to put as output in the data bus the value of the cell that is written in the address bus. And so after a certain time, in particular one machine cycle, Here you see this sausage, which represents a change in the line D78, which is my bake bus. Clearly, in this time, in all CPUs, in order to cope with slow memories, after asserting the bus and after asserting the read line, the memory would have had the option of raising a control line of the CPU, which is the wait line, which means I'm not yet ready. If the CPU, if the memory responds in this epoch by saying I'm not ready, the CPU is going to delay another cycle, another cycle, another cycle until the signal wait goes down, which denotes, which allows the CPU to understand that the data is actually ready. So it's like a traffic light that it's raised. It's all history. Similar, the writing to memory has to follow a similar pattern, like what you expect to be. You expect that if the CPU wants to write, once again, it puts on the address bus as output the memory address from where it wants to write, and then it will lower or raise the write pin and the memory request pin for a while. Like this, thus immediately signaling the memory that it wants to write to this address. Observe that there is a little bit of delay between the assertion of the memory and the assertion of the write. This little delay of half a clock cycle is to allow the signal to stabilize on the lines of the address bus. Once it's stabilized, the memory can read it safely, and so like the assert, the write is asserted, and then after a while, and then in this moment, the CPU will be putting the data out, and the memory will be reading. I mean, I think on the ZIT, the memory reads effectively the data when the write pin is raised. So the data is read in this instant, not in this instant. This lowering means I want to read, but when I lift the signal means now please sample the data. This is the game that allows once again the data to be stabilized on the wires, right? Normally, like still a CPU, I mean, this is a small lesson of computer architectures. Okay, now basically we know at electrical level what happens when we read and write on memory. How do we deal with peripherals? Well, the simplest way is to map the peripherals in the address space of the platform, which basically means we put address a peripheral as if it was a specific memory cell or a specific bunch of memory cells, and which are interfaced with the memory bus exactly as with the memory bus, which means address control and address data and control is exactly as if it was a RAM chip, right? And in this case, when the CPU wants to do something with a, let's say, serial port, it just writes a number or a bunch of numbers in a bunch of memory cells. The serial port, the serial controller would be smart enough to decode these numbers, which might mean instruction for it or states for it, and it will act accordingly. On many architectures, the I/O is slower than the RAM, and therefore they have a separate bus to deal with I/O in order not to clobber the memory bus and to slow down the entire machinery. Another fundamental concept which is essential in modern machines for those that did operating systems is the interrupts. Well, an interrupt is technically a signal, a pin, that if raised makes the CPU to interrupt whatever it was doing in that moment and to jump and to start executing a special routine, which is so-called user-defined and which is the so-called interrupt handler. Interrupts can also be generated not only by external events, but as you see, they can also be generated by softwares, and in this case they are called traps. But once again, and the classical trap that you find is the segmentation fault that many of you might have experienced when you program or you run C++ programs that do some mess with memory. Anyway, this is occurrence of an interrupt causes the CPU to start to save the current state of execution because it has to restart from where it has been interrupted into the stack of the process, and then to jump to the execution of the corresponding interrupt handler, which is a routine that has to deal with the event that has been signaled by the interrupt, and then once the interrupt handler is closed, the CPU presumably continues to execute from the point where it was interrupted. The interrupts are a little bit special functions because they can be taught, and in this course they will be taught as if they were regular functions, but from the assembly point of view they are not really, they are slightly different from the regular function calls, because when you invoke a function, you only have to save the status of the caller, or you only have to save the return address, which is the address of the next instruction to be executed after the function returns. In case of interrupts, you don't have only to save the return address, but you have also to say, let's say, the CPU status, which is a set of flags that denote what is the condition of the CPU when the interrupt was received. So in case of interrupt, you have to save two things: the return address in order to continue doing what you were doing before. Potentially then the interrupt handler will have to save the state of the CPU, but this is another story, so all the registers. But then also you have to save the CPU flags, and this is a privileged instruction. So in general, an interrupt handler ends with not a ret instruction that would only pop from the stack the address of the next instruction, but it will pop from the stack the address of the next instruction and the flags, right? From the programmatic point of view in C or in C++, you can denote that the function is an interrupt handler just by writing this line after the function declaration in GCC. So underscore underscore attribute underscore underscore interrupt. This is a non-standard, this is a compiler extension that tells the compiler to conclude that function with the return from interrupt. On IVR, there's a macro which is ISR event that can be used to basically write an interrupt handler. We will see examples of those. Another aspect that we can find in the CPU, in the modern CPUs, is the ancient CPUs, the DMA that I was mentioning before. So like what we have is that sometimes the CPU wants to interact. So some other device wants to interact, wants to have the possibility to interact with memory, or sometimes it wants to do it in tandem, in parallel with the CPU. This is particularly true nowadays, where the CPU are packed with a bunch of cache. In this case, when the CPU is operating with cache memory locally, it doesn't need to access the address bus. And so this is a perfect time for instance, for the disk controller to fill the RAM with whatever you wanted to read without slowing down the entire system, in fact, acting in parallel. So the DMA is so-called the direct memory access, is a strategy that does that. It's typically implemented by adding a bunch of signals, which are bus request and three signals to arbitrate the bus, which are: hey CPU, I want to have the bus; hey CPU, I'm done with the bus, right? If a peripheral says that he wants the bus, then the CPU, whenever it's available, raises a signal that goes to the peripheral and says, okay, now the bus is yours. The peripheral uses the bus until it wants, and then once it is done, it might release the bus by lowering a certain signal. Now, this was the story of microcontrollers. Now, what is a microcontroller? Is basically a system on a chip. So whatever you had seen in the past about microcomputers, now basically you can find 8-bit microcomputers or even larger. Even like there are microcontrollers that have, I don't know, 1 megabyte of RAM or even more. You can find them on a chip like of this size. So this is far more powerful, let's say, than the CPU of a Commodore 64. That was basically one of my first personal computer. Actually, it was under 28, but yeah. You have everything there. And why were they invented these microcontrollers? To build 8-bit microcomputers? No, they were invented because they are rather useful to replace complicated logic. Basically, they are intelligent devices that can run complicated programs that can be embedded in many applications. Like one instance would be, for instance, if you want to build a mobile robot that, mobile robot meaning the part of the mobile robot that deals with the motors, that has some sort of intelligence, meaning that implements some controller on the wheels, for instance, on sending the wheels, controlling the speed of the wheels in closed loop. If you want to have, I don't know, a device that reads a feed from the camera, meaning the camera chip, and packs the data into some sort of matrix, which is going to be the image, and maybe on this image already perform some calculation in order to return to the computer, to the smart device, some already processed data. Now, when operating with a microcontroller, there's a good and a bad. The good is that you have no operating system. The bad is that you have no operating system, meaning that you have the entire machine at your availability. Another issue is that typically you have rather little RAM, and certainly you cannot run a compiler on the microcontroller. You have instead to compile your program on your host machine and then upload it in certain way on the microcontroller. Plus, debugging is a hell because you don't have a screen attached to the microcontroller, and so like you lose the most powerful tool for debugging ever, which is the cout or the printf, in case we're talking about C programs. But however, there are ways to debug these applications with special debuggers that get connected to the chip. They slow it down, and then they allow you time by time what's going on with the execution of your program. I mean, in the old times, I'm sneezing. In the old times, a microcontroller to use microcontrollers, and this was the reason why I was especially frustrated. Let's say in the early 20s, because I needed to buy stuff, and I wasn't that rich, and so in order to operate with the microcontroller, okay, the microcontroller was cheap, but in order to program it, you needed to buy this special software that had to be connected with a special device that once again had to be connected with a microcontroller on the board. So like it was kind of a hell. But nowadays everything has become cheaper. So like you can easily get these programmers, which are devices that can be used to upload the program on a physical microcontroller for an affordable amount of money, let's say 20 euro, right? In order to program a microcontroller, however, assuming that you have your binary blob, so you wrote in machine language the program and you have it on a file on your PC, what the typical pattern was that you were connecting the programmer to your computer, connecting also the programmer on the microcontroller by specific lines, and then you were running a program on your computer that was talking with the programming device, and then this program was uploading through the programmer the data on the flash, on the non-volatile memory that is inside the microcontroller. Then once you disconnect the programmer, the microcontroller starts executing the newly installed program. Now, the good thing of modern machines, and I think one of the reasons why Arduino became so popular, even if there were already systems, is that it replaced somehow the need of a programmer, of a programming device. And it did so by basically loading on the chip a special program that is called a bootloader. And this special program can be activated by some special control sequence that comes from the serial line. So basically, outside of the serial line, before the microcontroller, there is some sort of chip that listens what bits are coming, and then if it detects a specific signal, it calls an interrupt on the chip, that then starts executing an interrupt service routine that puts the microcontroller in listening mode, and in this way it can read and write the flash. In particular, new architectures evolved by adding also another microcontroller on the board of the microcontroller that runs the bootloader itself. And this is the case of the Mega 250 that has another Atmel chip that is connected to the serial line that reads where it runs the microcontroller, and then if it is invoked, it gets all the bits that it receives from the serial line and it banks them inside the main chip to write down the data. So like here, I think I'll try to show you where is the microcontroller and where is so this is the main microcontroller, and this here is the small microcontroller where the bootloader is running. All right. Now, luckily, we don't have to care about microcontrollers. Now, talking about the AVR, the AVR, which is the chip on the Arduino, is an 8-bit microcontroller. It's a RISC architecture that has plenty of registers and that packs, in addition to the RAM, 8 fat kilobytes, and the flash, 256 kilobytes to store your program, a bunch of peripherals, like for instance you have plenty of serial ports, you have pulse width modulators, which are used to generate pseudo-continuous signals. You have a bunch of pins that can serve as interrupts. You have I think E2C receiver, so plenty. The good thing of this chip is that it has support for our beloved compiler, so both GCC and G++, which means that it can be programmed, listed both in C and in C++. I think in the slides I put a data sheet. Let's see if it works. Yes, it works. I put also the data sheet that I will not upload to the web page. If you want to read the wonders of the data sheet, if you want to read the wonders of this chip. Oops. Now, this is just to provide you an overview. At the core of the chip, there is the AVR CPU, which executes the instructions, which are 8-bit instructions. Then we have a bunch of timers. We have an analog to digital converter to read data from analog components. For instance, you could build, let's say, a rather simplistic sound card with an Atmel, with an Arduino. You have an EEPROM, which is something different from the flash. The flash is used to store the program. The EEPROM is like a non-volatile memory, which is accessible by the program itself. Once programmed, the AVR doesn't let the code to alter the memory. This is because it's a hardware architecture. This is a safety thing that it's typically used in also performance thing that it's used in the microcontrollers to prevent malicious code to alter the content of the program, so basically to prevent viruses. You can also install external RAM, but we will not do it. We will leave with 8 kilobytes of RAM. We have a bunch of timers that can be used in a variety of ways. Now, how to program Arduino? Well, the naive way, which we will not be using, is to install the Arduino toolkit. So on Linux, you could simply do something like that in order to install Arduino. Okay. Sudo okay, I have it installed. But if you don't have it installed, you do sudo apt install Arduino. And then to start Arduino, you write Arduino. And you have Arduino running, right? So this is a way to program Arduino. Arduino is an IDE. Oops. Arduino is an IDE that basically allows you to write C programs because that's it. In contrast, we will not be using this because I would like to teach you if we focus too much on the Arduino IDE, then you will be basically tied to this very specific kind of microcontroller, and I'd like you to see to be able to target any sort of microcontroller. So we will program at a low, like we will utilize still C++, but we will inspect the microcontroller on a without using all the sugar that it's provided by the IDE. To this extent, we need what do we need to operate to program this microcontroller without an IDE? For sure, we need a compiler, and for sure we need a program that talks with the bootloader on top of the Arduino in order to write our program, right? Now, the good news is that the compiler for that specific architecture comes together with the Arduino package, and so does the program for uploading the data onto the Arduino. So in our case, we could just be happy and have everything installed, even if there will be the IDE that we will not be using, which comes with the old Java machinery. We could be happy anyway by installing, by running this line on our terminal. I invite you to do so. Sudo apt-get install Arduino and Arduino MK. In this way, you will install two things: the Arduino IDE, which is the thing that we have seen before, and also a bunch of things which is called Arduino makefiles that will be used by us to define the building environment of our programs. For Arduino, we will not use CMake, albeit we could. We will just use plain make because it's simpler, and we will write very relatively small programs that don't need days of build time. Now, to see if we have the compiler installed, we can just write avr gcc. And it responds. It says fatal error. I don't have input files. So, which means that we have the GCC installed. Now, how to compile programs for Arduino? Well, it's quite for Arduino, for AVR. Well, we use it's a completely symmetric process to what was happening for the standard compiler. You, instead of writing GCC or G++, you write AVR GCC or AVR G++, right? So now let's make an example on it, and then while compiling at the same time, given that there is a plenty of microcontrollers, you might of the same family, so plenty of AVR microcontrollers, you have to inform the compiler about which specific microcontroller units of the family of AVR you are using. So if you're using the Arduino Mega, the microcontroller is the Mega 2560, and so you have to feed this additional option in this part of the microcontroller. Additionally, given that it's not a standard PC and that many routines are calibrated based on the known clock frequency, but the program does not have access to the clock frequency because the clock frequency is on the board, you might have to specify the clock frequency of your machine still in the options, and plus you can add everything. Now let's make a simplistic example just to play with. We open a program, we call it myAVR program in main. No. Boo. Boo. Let me do this, sorry, yeah? Nah, we do nothing. Just this is a stupid program that forever increments a counter, right? Stupid C++ program. It starts with the main routine and just increments this A variable. Observe that our stupid microcontroller, once it enters in the main, it will never exit the main, right? Now let's compile it. G++, and then I have to put the flags that I never remember. This flag over here. This flag over here. Then -O. My AVR program. I invalidate in a clue there, yes, right? Well, let's remove this AVR. I mean, today I'm okay. We have presumably we have my AVR prog. Now let's see what file is it. It's a ELF executable for an atmel blah 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 statically linked with debug info not stripped. Very good. So like okay, yeah. All right, guys. So like it's good because we have a way to generate binary, only that these binaries cannot be executed, and also only that this program is quite useless because we do not yet have a means to execute the programs on the AVR. So okay, so this is just to show you that once you have a compiler, you can take the same program and compile it for different architectures. All what you will get is different binaries, but these different binaries, well, if targeted, if put in the correct machine, then they will lead presumably to the same results. Now, once we generated the program, if you remember what the command file was telling me, the compiler instruction, that is this one that I have executed, no, what was the last one? Yes, this one. This was the compiler instruction, the time that I called the compiler, basically, produced me my AVR prog. And then I ask, hey, what is my AVR prog is? Well, it tells me it's an ELF executable, which is one of these binary that contains a lot of information also on how the program has to be loaded in memory, right? Now, wonder what this for a microcontroller means. And in order to send this program to the microcontroller, we typically need to convert it into another format that contains also instructions for the bootloader, for the programmer. For instance, that tells that basically that has to take the ELF file that contains quite articulated instructions and turn this ELF file in a set of instructions for the program that controls the bootloader. In particular, this ELF file should be we need to add information to this ELF file specifying, for instance, what do we want to write on the EPROM or when the microcontroller will be written, or specifying, for instance, physically, the bootloader is a very stupid program, physically from which flash location we want the program to start to be uploaded, and so on and so forth. So this is typically done by another program. Shift F5. No. Yeah. This is typically done by another file, which is AVR object copy. Well, what it's typically doing is you just like ignore it, and you always use this, you just ignore it and you always use this line, AVR object copy, where the output is a file name that ends with the hex destination, which is ready to be fed to the microcontroller, to the bootloader, and the input is an ELF file. So basically we're doing what the operating system is doing when it loads a program. We have to convert it into some sort of memory image. And this is done with AVR object copy. This is a bunch of options, but we just copy these options. What we do here is that we convert the ELF file generated by the compiler into an hex file that can be then fed to the final programmer, right? So stage of compiling for Arduino is 1, generate the ELF with the compiler. Stage 2 is to generate an hex out of the ELF, and now we're gonna be doing it here. AVR object copy minus what was it? Minus, I never remember the options. The options were here. X. Okay, and then this program generated another thing, which is myprog.hex. How does this look like? I'm opening it with an editor. It's a bunch of hexadecimal numbers. This bunch of hexadecimal numbers, they contain, like they are lines that contain, this is clearly a control sequence, I think. This is the address, then there will be a control sequence, and then at the end there will be the instruction to be written in that location. Right? And this is something that the programmer can digest. What is the programmer on the PC side? How do we call the programmer? Let me go back here. How do we call the programmer? The programmer is called AVRDude, to which you have to pass a multitude of flags, but the only important flag that you have to remember is this. So the port where the microcontroller is connected. This is the serial port that will appear once you connect the Arduino. And then you have to write the file name in here. Like, this is horrible. It's a command line that no one ever remembers. But the good thing is that the good old Giorgio made for you a makefile that you can use to do automatically all these operations. The only thing you need to do in this makefile is to specify these 3 lines. you have to specify the object files, which is basically the CPP files that you want to, that constitute your program. So they might be, they have to be called exactly as the CPP files, but they have to end with a no destination. And then the binaries, because out of a certain folder you might want to generate multiple executables, like for instance main1, main2, and so on. So these all are independent executables that can be loaded once at a time on your microcontroller. And then at the end you have just to write include AVR common and K. So let's see how this might work. And then this is gonna generate the entire process for you. Okay. So, but of course, you'd like to see me invoking, no, never. You would like to see me invoking the uploader to upload the program on Arduino. Remember that now we have my avr_prog.x, and I'd like to upload this program. How do I do? Well, I copy this horrendous command line. Where was it? Here. Mama, horrendous, horrible. Okay, of course I have to remember that the file name here has to be replaced by this, right? Then the next step that I'm gonna do is to connect my Arduino to the machine. I have my Arduino here, and then I press enter. And then I press enter, and it says, I can't open the device of resource busy. Let's see. Where's this show? No, I can read and write. Let's try again. Yeah. No, it's not cooperative. Ah, it went. It managed. It managed to write on this precious microcontroller my program, and it. Okay, I needed to do this couple of times, probably because I needed to wait the system to recognize the Arduino. All right. Like what happens is that it wrote this 288 byte of flash, which constitute the program onto my machine. Right. Now if we want to do this in a more fancy way, we could go cd robot okay source or 309 lesson test. I'm just creating another folder, I call it lesson test, where we will put all the things, and then we have to create a make file in the same folder. What were the instructions of my thing? Okay, I need to write objs and bins. Bins is equal to avr. What was it? The name of the program? My AVR proxy. And that was it. And then the other thing that we need to do is to include this thing. Oh, see? Let's see what happens. Ah, it worked. I type make, and I have my avr_prog.o. Is it? Let me see. Let's see. if the destination was correct. Ah, no, elf. It has to end with an elf. That was a mistake in the slide that I'm gonna fix immediately. Sorry guys, you have to end with an elf the programs, because it's an elf the binary. Oh, and we have my avrprog.elf, right? Now let's say that I want to upload it. You can simply do make avrprog.x, and it has been uploaded, right? So that's all when you need to use my make files. That's easy, and then in this way you have basically we have introduced how to use this infrastructure to work with AVR. An important bit that you will encounter is that once you connect an Arduino, you don't have the permission to access the serial line groups. So in order to, because the serial line is something which is a resource of the computer, and a standard user cannot access the serial line. Only users that belong to the group dial out can access to the serial line. So in order to be able to use, without using the root permission that you should never do, in order to be able to use the Arduino by living comfortably in your user space that doesn't make you destroy the machine, you have to add yourself to the dial out group. So let's say that your user is Gino, you would have to do sudo add group Gino dial out. But it says the user Gino does not exist. Of course, you replace Gino with your username, and then you will be able to access the Arduino. After that, maybe a logout and a login might be required. All right? Very good. Now, that's a horrible thing. Debugging is basically impossible. So now so far we can use and we can run our funky C++ programs arbitrarily complicated on an autonomous low power 8-bit microcontroller. This is fantastic, only that we will misuse the RAM like hell, so we have to be particularly careful. Now for debugging, I provided you a version of printf. I don't know if you know what is the printf. If you don't know it because it's a basic way of printing strings. The printf that I've implemented allows you to write on the serial line that then you can inspect with a program which is called Qtcom. For this purpose, to help you with the bootstrapping, we provided you our first AVR program, which is in the list, is 00lo avr.cpp, that basically uses the print. Remember that we are living in a microcontroller. You just like copy this header of things because we need it for interacting with the AVR. Before using the printf, please call the function printf init, because if you don't do this, the UART is not initialized and you cannot write on the serial line. But then after that we have our fantastic printf function, and then here we're instructing the system to print hello, to print an integer, which is the first argument we're giving, and to wait 100 milliseconds. Now, what happens if we upload this program on our AVR? How to upload the program? Well, it's called hello AVR. I will have to write make. With make, I have compiled it, and then after compiling it, I can upload it. To upload it, you have to do make hello avr.x. Very good, I did it. I uploaded my program. Now, if I would open the serial line, what would you expect to see? Let's do it. Qtcom is a program to access the serial line. I have to configure it to this baud rate. I open it, and then I see hello. which is basically, ciao Arduino, I like to write silly things. This was me, because you can also write to the, you can, there's also a scanf that I implemented to communicate with Arduino, but yeah. All right, so this was our first program. No. Yes, this was our first program. Now, in this half an hour, let me talk about peripherals that you have onto the ADR. We have serial ports, we have analog to digital converters, we have PWM generators, we have timers and digital ports. All these devices are memory mapped, and that they can be configured by writing something in the corresponding registers, which are just variables. You can read the datasheet if you need to do something. We will start with something which is rather simple, which is the digital port. The digital port is basically a digital pin that can have a value between either 0 or 5 volt. A digital port corresponds to a specific bunch of pins on the Arduino, like pin 1 to 4 are pin 1 to 8, let's say this way is port A, pin 9 to 16 is port B, and so on, right? Of course, on the Arduino Mega, the mapping between the pins and the ports is kind of cumbersome. You have to consult the pin mapping of the Arduino Mega to discover which pin of a port corresponds. So to each port, and a port is a collection of 8 digital pins, is associated to 3 registers, which are accessible as if they were 3 variables from your C program. These 3 registers are the data direction register of the port, so we will have data direction register A, B, C, up to L for a certain port. And then each bit of this data direction register controls whether one of the pin of a port is set as input or as output. If it's set as input, that pin is in high resistance mode, and then you can basically you can't write on that pin, but it's accepting values from the outside. Okay, if you set it at 1, that pin is used as output. If you set it at 0, that pin is used as input. You have another bunch of, and this is the data direction register. It's used to configure the port. So what do I want to do with each individual pin of that port? You have another pin, which is the port pin, that is the another register, which is the port register, which is used to write a value on a port. You can also write a value on a port that it's configured as input on a pin, a value that, so you can also write value on a pin of a port that is configured as input. In this case, you are altering its default level. If you set this bit to 1, this means that you are putting a pull-up resistor, that you're saying, oh, if this pin is floating, then please read a high value. Then we have a pin register that it's actually the port where you read from. Okay, port is for writing, pin is for reading. So if someone sets the bit number 1 of port 7 of port L at 5 volt, and you have configured by setting the bit 1 of the data direction register of the bit 1 to be an input port, then you will be able to read from this variable that the bit number 1 is set to 1. Conversely, if you lower the voltage to that pin and then you read from this variable, then you will read that this value is set to 0. That's it. Then I have a question: do we have to buy an Arduino 2560 or it is not necessary? Do you have to buy some additional components? I mean, guys, a 2560, so I'm answering now to Antonio. If you don't have already a 2560, buy a 2560. Don't, I mean, it's absolutely not necessary to buy an original 25.0. You can buy, there are alternative brands which are way cheaper, and then I think you can find it for as least as 12 euro. You can buy such board for 12 euro or 15 or 13 euro. I mean, you can consult with my PhD students because they always try to buy the cheapest possible on the market. This was the answer to Antonio. Like, and then as for the components, you don't have to buy any other components. You can be happy with a pair of wires. Wires are wires like that. But if you don't have such wires, right, then you can easily live with you know, the bread. When you buy the bread, I'll show you. If you don't want to buy such fancy wires, you can get, you know, I hope you see what is this. This is one of these like plastic and metal things of the bread. You peel it and then you can use it as a wire, because that's all we're gonna do, like, let's say, in terms of peripherals. But then if you want, and if you have fun and you want to build your own robot and stuff, then you can buy all hardware you want, right? But the Mega 560, I'm sure that the operating system guys that are attending the lesson will be able to advise you on Telegram that on what is the cheapest option. So all I ask you to do is to invest this I don't know, 15 euro. And also, like, you can also ask the people that of other years that don't use anymore the board to sell you their board. I think then you can get it even cheaper, and we don't produce electronic waste. All right. So said, I've given you I've given you the principle of an accessing a port. Now, we would like to implement our first program that basically toggles an LED every second. So every second it toggles the LED. There's one, there are 3 LEDs on the Arduino, but it toggles this one LED on and off every second, right? It's like, how do we do it? I mean, logically, what we will have to do is to first discover where this pin, this LED is connected. Second thing, once we discover where it is connected, we will have to figure out to which bit of which port this pin is connected. And then, once we have figured out that, we need to configure this pin as output. We have to say, to set a 1 into the data direction register of that port in correspondence to the pin that we want to control, because we are writing on or off on the LED, right? And then the third thing, then we will have to enter in our ugly endless loop that at every cycle toggles on or off that particular pin. How does it do it? Well, it writes something on the output port associated to that pin. In particular, it writes something on the output port. So what do? First, we discover where is connected the LED. We click here, which is here. No, terrible. Right, this detach, put here. No, yeah, it's not cooperative. I know it, is that OpenOffice takes over. If you click to the link in the slides, you will figure out that there's the digital pin 13. Digital pin 13 is connected to the LED. Yeah. Somewhere, LED, let's see, Control F. No. LED, or then we ask Google. We ask Google, blink Arduino. Oh, okay, yeah. Okay, the LED built-in is connected to the pin 13. That's what it says, right? To the pin 13. And then we have to go to this ugly thing and discover that the digit... Oh my God. Now you understand the pain of digital pin 13, eccolo qua. Digital pin 13. Right. That's what we have found. Because on the board, the pins are numbered differently from the microcontroller. This is brilliant, guys. And we figure out that the digital pin 13 is connected to the port B7, right? So now, finally, we figured out that this bloody pin is connected to the port 7, right? So, port B7. So now, let's go to the slides, close this business. Here, Shift F5. So what our program will have to do, port input value, LED blink, port 7. So now what we have to do is to configure the data direction register. So we build a mask because we can only read 8 bits at minimum. uint 8t is basically a way to say an unsigned int of 8 bytes. It's in the header standard int, and we call it mask, and then we take 1 and we shift it by 7, and this way we enable. We have a value which is 1 0 0 0 0 0, 1 with 7 zeros followed by 7 zeros. Then we can configure the pin as output by masking, by sending, by assigning to the data direction register the port. Here I did an OR equals because I only want to stimulate that particular bit, but you can also do an equals. And then we enter in our endless loop, and basically this is my implementation. You have an integer k, could be also an unsigned char k, and what you do is you increment at every loop this k, and this instruction here basically picks up the last bit. The last bit of a digital number goes from 1 to 0 all over and over. Every time you increment it, it toggles between 0 and 1. In this way, we can figure out whether we are in an odd case or in an even case. If we are in an odd case, so if we have a 1, we set the mask, which is 1 followed by 8 zeros, to the port B. If we are in an even value, then we set the port B to 0, and then we switch off our LED, and then we wait for 1 second. Let's see what happens on our fantastic machine if we upload this program. Oops. How long do I have? I still have 20 minutes. So what do? I go into LED blink, LED blink dot health, no hex. Okay, now what I expect to see, yeah, unfortunately it's very short, but maybe you see something. Do you see a blinking LED? Or let me zoom. Yes, there is a blinking LED. But in the program, if you read well, I was also printfing something on QtCom. So if I would open QtCom, and on the serial line, I would be able to read what the program is writing while it's obsessively blinking the LED. QtCom opens. I open QtCom, clear. LED 1 0 1 0 1 0. Right? Very good. Now we have done that. Let's move to the next thing. Now we are able to output some value on a port. Now clearly, if I would tell you, hey, please write on the bit 6 of port B, you would easily be able to replace this program and put in here a 6, because you have just to shift the 1 by 6 in order to generate the mask, right? Shift F5. Now, next program. For this program, we need a wire. So for the course, we need 2 wires. No, 2 wires. They can be either this way or this way. No, they are the same. To this extent, we need pin 12. And then what we would like to do is to read constantly from a certain pin. And we will use the pin 12 of Arduino. It's the digital pin 12. And then we have to figure out where it is connected. Still, once again, looking in that ugly documentation. Well, if you do that, you will figure out that the pin 12 is connected to the bit 6 of port B. So in this case, we have to clear, the configuration proceeds as follows. First, we have to say to the machine that we want to read on the bit 6 from the bit 6 of port B. So we write, we create a mask which contains 1 in position 6. And then we negate the mask with this not. We basically flip every number which was 0 to 1. In this way, we would have a 0 only in the location where the bit 6 is, to denote that we want to read. I recall that if we want to read from a pin, we have to set 0 to the data direction register of that pin. And then we want to perform an AND operation, a bitwise AND operation, with the values already contained in the DDR-B port, which is the data direction register of the port B. Basically, by doing so, we set to 0 only. We force to 0 only the bit 6, and we leave all other bits unchanged. That's the game. Then, in order to make mess, in order to have a defined output, that when the pin is disconnected, we read a 1 from that pin. What we do is we set to 1 the bit 6 of port B. And then finally, we enter in an endless loop, as always, where we read with this pin B. This is a variable. We read from the input port. We have to read the entire 8 bits, but then you have to consider only the bit number 6, and therefore you will have to perform a bitwise operation with a mask which is consisting of a bit 1 in position 6, and then this will tell you whether this number is 0 or not. And if it's 0 or not, you basically toggle this variable that you called key. This is a Boolean expression. Basically, you take pin, you bitwise end it, and you assign to the variable int, or the bool key, the outcome of this operation. Right? I mean, it's a C program, but if you write bool and you change the destination, then it will become a C++ program. And then we print the output. We print what we are reading on the standard output, which means on our serial line the status of our switch, right? Particularly, we print the switch. We print the status of our pin, and basta. All right. So let's do it, and then let's go to the exercises. Let's test this program. Let me convert it to a C++ program. Shall I? Let's find it C. Mac digital in.hex. Now I uploaded the program. And so what I need to do is to stimulate the pin number 6 and ground it. So I will have to put a cable into the ground. There's plenty of pins with name ground. And then, no, the pin 12. and then I will have to, disturb the pin 12, and that's what I'm gonna do in this moment. After opening QtCom, obviously. QtCom. Pin 12. Okay, this is clearly periodically printing me the thing. Okay. I have the pin out. I have the pin in. Out. In. Out. In. Out. In. Okay. So it's interesting. So we are able now to report from the PC whatever we want. No. We have done plenty of things, and then now I propose you for the next time, I mean, of course, there will be someone that has done it, 2 exercises of varying difficulty. The first exercise is the shaft encoder, and the second exercise is the keyboard matrix. Okay, the shaft encoder. The shaft encoder is the encoder that you find attached to motors, because actually our... Oh! I have to repeat everything. Guys, please tell me when I... yeah. Okay, I unfortunately there is not the... Marco, can you tell me when you stopped seeing the screen? Or any of you, can you tell me when you stopped seeing the screen? And then, of course, I will edit this part and repeat everything. Because I cannot go back. So it was 10:42. Okay, it was 10:42, so I didn't say much things so far. We have only lost 5 minutes. All right, we were talking about digital ports, input value, right? The LED thing, since the LED thing, perfect. So the LED thing, all right. Okay. So now let me repeat the digital ports business. Now we have seen that we are able to write. Now let's see if we are able to read. In order to read, we Shift F5. In order to read, we will have to do the dual thing. So first of all, we have to select a pin on our Arduino that from where we want to read, and we choose it to be the pin number 12. By looking in the documentation, we figure out that the pin number 12 is connected to the bit number 6 of port B. And the very first thing that we have to do is to configure this pin in order to actually read values. In order to configure a port, a digital port, to read, we have to act into the data direction register. So technically what we have to do is to set the bit number 6 of the data direction register to 0. And now in order to do so, we generate a mask where we put a 1 in the bit number 6 of the data direction register, and then we negate the mask, so we get all 1 and 1 0, and then we do a bitwise end in the value already contained in the data direction register. Basically, this operation ensures that we are setting to 0 only the bit number 6 in the data direction register, and we leave all other bits unchanged. In addition, what we would like to do is to leave the port how to say the other, I was reading the chat. The other option is to put the default value of a pin of the pin number 6 of the port B, which corresponds to the bit 12, to a high value. In this way, when the pin will be disconnected, when we are not stimulating that bit, we will read a logical 1 from the pin. Now, since the pin, when it is disconnected, reads a 1, in order to alter the value, we have to lower the value of the pin, because we have pull up that sets it to default 0 volt. In order to basically see something, we need to ground it. So we will use a wire that we will put on the one end, we will put it on the ground, and on the other hand, we will have fun playing with the pin number 12, right? So in order, of course, to appreciate some difference, we need to put it to pull up by setting 1 to the bit 6 of port B. And then we enter in a while loop. When is it that the wire is inserted? The wire is inserted when the bit number 6 of the pin went from the bit number 6 of the port B. I'm reading a logical 0, because this means that I have inserted a wire, and this means that I have shunted it to ground. So when this happens, when the pin number 6 of the port 0 is low, then I read a logical value of 0, right? And so this number is 0, so this Boolean expression is true. And I just call it a key pressed, let's say, okay? And then for fun, I also print the entire, no, that was not port B, was supposed to be pin B. I want to write on the output, I could also print the entire value of the port B in hexadecimal and see what happens, right? It's like basically by running this program, I will be able to see what I'm doing on the Arduino by inserting and removing this wire, which is on the one end connected to ground, and on the other hand is connected to the pin 12, yes and no. All right. Now I will modify slightly the program on the binary. Is it this? No, like blinker, not interesting. Emacs 02 digital in.c. We'll modify it a bit because I'd like to see pin B, and I will print in hexadecimal. No, 02x. So I'm reading in hexadecimal value all the pins of the port B, just for fun. I can also, yeah. I uploaded, and then now that I uploaded, I can now that I uploaded, I can open QCOM. Open. Okay, this is what I open QCOM. I put QCOM so that you can see. Right now, if I lift I disconnect the pin. Now I have connected I have shunted the ground and pin 12. Now I lift the connector. I shunted, lifted, shunted, lifted, shunted, lifted. Now, of course, I could modify this program trivially by reading from all values of port B by configuring the entire port B as input, and then in this way I would be able to read all bits in once, right? This is something I could do. Okay? Very good. If there are questions, I'm gonna answer. I mean, let me do a simple example on how to modify this program to read all pins of port B. We set all pins to 0, given the or I can simply 0, 0. We don't even need the mask. We don't need the mask. Then I will have to undo all these changes, obviously, otherwise it's not compliant with the slide. We can delete this. We delete this. We delete this, and we're done. Yeah, it has to be a bloody... of course I have to disconnect Qtcom, because otherwise it's gonna mess with the... Start Qtcom, and let's see. Open. Now, sorry, there is something which is pin B, DDR-B, and port B. I have to enable the pull-up resistor. Make better. And then start Qtcom. Always on the other window. Open. Okay, this is what I expect to see. I'm reading FF from the switch. Hope you can see something. Now I'm gonna stimulate, I don't know, the pin number 13, 7F. I'm gonna stimulate the pin number 12, BF. And then I'm gonna stimulate the other, DF. Oh, they are quite regular, I'm impressed. I'm gonna stimulate the other pin, EF. Oh, all right. Of course, you can generate any number by putting on and off the pins of the port, right? So we also are able to read from an entire bits of a port. Now, we have two exercises that I'm proposing you. The first one is to do a shaft encoder. Shaft encoder is that thing that is attached to the wheels and tells you whether they are, how much they are moving. Basically, a shaft encoder comes with two signals, and it is decoded by this state machine. What you need to implement a shaft encoder is two pins, actually two of those, right? Two of these wires, so buy bread, so eat bread, and what happens is basically these two signals, I think I've already explained it, they follow the following transition. They go from 0, 0, if the motor is rotating in one direction, they go from 0, 0, then 0, 1, 1, 1, 1, 0. And therefore, at every transition, like when going from 0, 0 to 0, 1, from 0, 1 to 1, 1, from 1, 1 to 1, 0, and so on, you increment by 1 a certain counter. In contrast, if you go in the opposite direction, so if you go from 0, 0 to 1, 0, from 1, 0 to 1, 1, and so on, so you go in the other direction, you decrement the counter at every state transition. So you have to write a program that configures two digital pins as input, and we have done it, and then it periodically monitors, but really at high speed, periodically monitors the state of this port, and then it figures out whether the state of these two pins at the previous instant is equal to the state of the pins at the next instant, and at the current instant. And if this is the case, or if these two pins are different, then it checks whether it has to increment or decrement the counter. Okay? And of course, the program writes something on the serial line with printf only if something has changed, because if nothing has changed, otherwise we are gonna club the serial port. Sneeze. Okay, this is the first exercise that I propose, and then there is a second exercise. This was the shaft encoder, and then there is a second exercise which is cooler, which is the keyboard matrix. It can be still used. This is a more difficult exercise, and it's optional, but we will demonstrate it next time. It's how to read by having only 8 bits, how to read from 16 keys, basically. Of course, you don't need a real keyboard. You can sufficiently live with one single wire to test this exercise. Of course, also for the encoder, you will have to use 2 wires to simulate the 2 pins, or the 2 signals coming from the encoder. Now, in this exercise, basically the game is that you read each line of the keyboard sequentially. So now, this is a keyboard, or this is a keyboard matrix. You have a certain number of pins as input. Let's say these 4 so these 4 bits are controlled by you. So you can decide which value to put on these 4 bits. And these 4 bits here are not controlled by you. So you cannot see which, you cannot impose a value on these bits. Now, to read a keyboard matrix, what typically is done is to use a circuit like that. And what happens is that you can read in one instant at most one line of your keyboard matrix. Technically, what you do is to set all bits of your keyboard matrix to 1, but you set to 0 the bits of the keyboard matrix that you want to read. What would happen then is that you know which line you're lowering. What would happen then is that if you close a switch of one of the keys of this line, if you set a 0 here and you close the switch, you will read a 0 on all the bits for which you have pressed the key on this line, right? So if you close the switch and you set the 0 here, then you're able to read the 0 here. In contrast, if you have a 1 here and you press a switch, then, or if you don't press a switch, then you have a 1 here, right? Okay. All right, guys. So if you have you will be, the message is that you will be able to read only the line for which you have a 0 here. So you will have to loop a 0 1 1 1 1 1 0 1 1 0 1 1 0 1 and so on this port. So shifting a bit, and then whenever you have a certain value of configuration on this port, you will be able to read. You will sample from the other part of these bits. And you will figure out that you have a 0 only on the keys that have been pressed that correspond to the row for which you outputted the 0 over here. Marco says, when the vertical and horizontal cross, there is a bridge, of course. So like, if you see a cross here, these wires here, they are not connected. There's a connection only if you see a ball. This is the answer to Marco. Says, there is a connection here? No, there is no correct connection. The connection is only where you see a ball. Okay, so these are on 2 different levels, these 2 wires. Okay? So now, it's kind of interesting to implement the keyboard because this is exactly the very same routine that was implemented in the first home computers to read the keyboard. And yeah, the circuit is relatively simple, no? If I have a 0 here, then and then a 1 everywhere else, well, if I press a key here, on this line, I will, if I have a 0 here, I will be only able to read this line. If I have a 0 here, I will only be able to read this line and so on. Okay, so you sample the line once at a time. And if I would have to implement this program, I would check which key in this row has changed the status with respect to the previous instant, and I would output only an event to the serial line. So to this extent, I could use basically a 16-bit value. All right, this is the second exercise. And then this closes this lesson, which was a little bit longer than expected, but next time we will see the solution to this lesson, and then we will go on with the second part of the AVR, and then we will implement a closed loop motor control, presumably on Thursday. Yes, that's it. Have fun, guys, and yeah, all the best. If you have questions, post them in the chat. Or we will discuss